Okay, today I will talk about some results I obtained during my PhD work, which is based on recycling industrial byproducts and other wastes, other industrial wastes. In particular, we have this collaboration with the company, Italian company, Italium, which has a refining plant of end-of-life oils, in particular engine oils, which are regenerated and they put again on the market. In particular, as you can see here, this is a simplified scheme of the plant, and you can see a pre-flash where the oils are heated up to 140 degrees, and then they go into a thermodeasphalting column, which works at 360 degrees and at low pressure. And in particular, you can see here that the base product, the bottom product of the column, is this refined engine oil bottom residue. These are other products which are more which has a market on Italian market, but also international one. And in particular, this residue is the base I used to obtain a new binder. And also I used other wastes derived from this process, which are not shown here because it is the plant is more complex than this, but I will summarize in the next slide. Okay, the recycling option starts with this product, which is called Viscoflex 1000, and is the Reob product I showed in the previous slide. Here is 160 degrees, okay. Then another waste derived from the plant treatments of the oils, of the exhausted oils, is this selite waste, which is a diatomaceous earth, okay, and is used to filtrate to refine oils. Then we have another particular waste, which is an exhausted alumina catalyst, which is used to remove some metals from the end-of-life oils that that feeds the plant. And here is dehydrated sediments, which derived from the centrifugation process of the oil, of the end-of-life oil. And this was dehydrated by using calcium oxide, okay, because this one is not solid, but it is a liquid with it's an emulsion with water, okay, oil and water. And the last one, but this is not from the plant, this is from another industry, Ecopneus industry, and this is the crumb rubber waste, which was mentioned previously in the presentation. Okay, this one were used to create a circular economy process, a recovery process, to produce a new finished bituminous product, an end of waste. This one will we hope that this one can substitute the bitumen derived from petroleum, crude oil. Okay. For example, next step is to use this finished product and the RAP, the reclaimed asphalt pavement, which contain a percentage of aged bitumen, to create a new asphalt, concrete asphalt, that could be used to pave the new streets. Okay, this in particular, the reclaimed asphalt pavement that has an oxidized bitumen could be mixed with some rejuvenating agents to restore the structure, the original structure of the bitumen. And all these circular economy process. Okay, the work planned during my studies is represented in this slide. Here you can see the first step, in which we characterize the binder from a chemical physical point of view, and then we, in collaboration with the University of Bologna, made some engineering study on conglomerate characterization using a RAP as a base material. In particular, as you can see here, from a chemical point of view, the bitumen is composed of an aliphatic zone, hydrocarbons, saturated hydrocarbons, and an aromatic zone mainly composed of molecules, asphaltene molecules, whose structure is like this, shown in these pictures, which is archipelago structure, for example, or island structure. And this is, as you can see, this is very low peak in the NMR spectra. From an FM point of view, as discussed by my colleague Abram, you can see here the structure of an asphaltene in the bitumen, and these structures, these B structures, represent the asphaltene materials, the aggregates that gives to bitumen the rheological and mechanical properties. In particular, the study of this new material with the Viscoflex 1000 represented here, as you can see, it consists of only of on a viscose modulus, G second, compared to a classical paving bitumen 5070, which has a viscose modulus and an elastic modulus and a tangent modulus, a loss of a tangent modulus, tangent delta. Here is a modified SBS bitumen, and as you can see, the transition temperature is very high. It's about 110 degrees respect to an unmodified bitumen, which is about 60-65 degrees. The Viscoflex, which is the product I used, has no transition. It has no viscoelastic properties. It is completely viscose. The goal is to transform this in a situation of a modified bitumen. In particular, as you can note here, the modified bitumen with a polymer, SBS in this case, shows a buffering effect in which the tangent delta remains practically constant during a wide range of temperature. Okay, and this is very important. Now, the first step is to create a binder formulation. In particular, as you can see here, the rubber used is from Ecopneus, is a end of waste rubber from wheels. This is the Viscoflex from the Italian Regeneration Company. These are two kinds of products, but I will concentrate more on these. And these are other additives. Waxes are used to soften the product, to give some soften properties. The goal is to completely eliminate the polymer, or reduce it as much as possible. Today it is used to modify bitumen in a percentage of 5, 8, 10%. And here the goal is to create something that this could be very, very low or absent. Here in the table, you can see the formulations I create using Viscoflex Viscoflex 1000 and Viscoflex 2000. In particular, Viscoflex 2000 I use it principally. The R stands for rubber, and these are the percentages I used. Okay, wax are these. The SBS polymer, as you can see, is used only in these two formulations. This is an adhesion promoter here, and it is used to improve the connection between the bitumen and the conglomerates and the aggregates. P2 and C2, CDN and CNC are waste products derived from paper wastes. They are cellulose byproducts, okay, derived from some industries, waste papers and so on. RP and NT are other natural additives that I used. In particular, RP and NT is used only in one formulation as LES. These are the conglomerates prepared at the University of Bologna. Here are thermostated in water for a test. And as you can see here, the main test to discriminate the possibility to use a formulation, one of these formulation here in the left of the table, is the ETS modulus or ETMS and ETMS modulus. As you can see here, for a polymer modified bitumen, a hard modified, an ETS modulus is 0.90 and ITMS modulus is of over 4,000. If you use a wrap bitumen with a classical bitumen, you obtain these results. Okay. When I use the binders prepared as explained in the previous slide, I obtain these results showed in the table. The most interesting one are these one. Okay, blend 26, 27, 29. Blend 26D means that the product is the Viscoflex product is a dense one, because there are some different kind of products. And V1 means Viscoflex 1000. Okay, as you can see, this one are higher than the polymer modified bitumen. So in the next slide, for example, these bitumens, as I said, are obtained using 100% of reclaimed asphalt pavements, except the ones indicated as CAM, that are a mix of virgin aggregates and recycled aggregates, okay, that are commonly used today to prepare asphalt conglomerates. In this slide, I report the results of the previous table, and as you can see here is the polymer modified bitumen, okay, and these are the results of the blends prepared using the Viscoflex product, which I remember to you that it has no elastic modulus. It is completely viscose, okay? And as you can see, we create a binder that has very interesting properties, because the objective is to obtain a ETSM modulus at 20 degrees higher than 4000 megapascal, and an ETS modulus higher than 0.7 megapascal, because these are Italian requirements for road construction, okay? And as you can see, some of these blends here, for example, these are in the satisfy the conditions. Okay, there is a problem, but I worked on it, and I prepared some other blends, because some of these blends has a very high ETSM modulus, which can create problems of stiffness, a higher stiffness, okay?
Проблеми для жорсткості, більш високої жорсткості. І отже, я, наприклад, ця була дуже висока, і порівняно з цією, але я підготувався під час другої своєї частини своїх досліджень.
This problem. And I'm waiting for the mechanical results to see if these properties has improved or not. Okay, but I think this research is very promising. In particular, as a work in progress, we try to prepare a new blend to comply ANAS parameters, and substitute elastomeric polymers with new agents, naturals, possibly from natural sources, and to obtain new low-cost and eco-friendly blends that can substitute the bitumen from crude oil. And in particular, this is to obtain a blend that mimic the polymer modified bitumen, and a bitumen 5070 ideal for cold asphalt production. And this for now is a part of my research activity in the PhD, during my PhD research. Thank you for your attention.
Дякуємо, Мікеле. Дякую. Це революційний крок, як на мене. Ви отримали патент.
Excuse me, I don't understand. Can you repeat?
Я говорю, що це досить такий революційний крок в розробці в'яжучих. І чи отримали ви вже патент на свій винахід?
Okay. Not on this topic. We got a patent on the industrial process, because I spent 6 months in the Italium company, working on this and preparing these blends. But I solved an industrial problem, for example, recovering the waste, the centrifugal waste, by dehydrating their wastes, because they actually sent to an incinerator, and now they can recover it, because I took off the water by dehydrating using a simple reaction, and it is possible to recover this in the formulation, a bitumen binder formulation. Okay,